This is page 4 of the worksheet for lesson 4.1 for Calculus A. I should have really included numbers 12 and 13 with the last video because it's all part of the same problem. But basically, it's looking for the relative maximum value and the relative minimum value of a function. So the relative maximum and the relative minimum are basically the tops and bottoms of hills. So on the last page, I used the function x squared plus 4x plus 4 on the interval -4 to 0. I took the derivative, and there was a 0 at -2, and so there was a critical point at -2, 0. I plugged in the end values for the interval. -4 got me 4, and 0 also got me 4. So basically the function starts at 4, goes down, hits -2, 0, and comes back up to 4. So remember what I said, that relative maximums and minimums are like the tops and bottoms of hills. You can't just have it in an endpoint, or at least that's what some people's definitions are. We're going to go with that definition, that it can't be at an endpoint. So the relative maximum for this problem doesn't exist. The relative minimum, however, is right here. It's at the point -2, 0, so the relative minimum for my problem is 0. And again, because these are absolute maxima, but they don't come back down, they're endpoints, so the relative maximum does not exist, at least for my problem. So for number 14 and 15, we are looking for intervals on which these functions are increasing and decreasing. The key to finding that is to first find all the critical values. To find critical values, you look at the endpoints. If you're given an interval, it looks like for these, they're the whole domain. So we'll also look for places where the derivative is either equal to 0 or not defined. After we find the critical values, we will also look at x values in between the critical values, plug them into the first derivative function. If they are positive, the function is increasing on that interval, and if the derivative is negative, the function is decreasing on that interval. So 14 being a polynomial function, I chose a polynomial function for my example. So the first thing I did was take the first derivative of the polynomial. Then I set it equal to 0, I solved, and I got 3 places where the derivative is equal to 0. So these are most likely relative maximums or minimums. I plug these values back into the original function, and so I've got points at 0, -3, -1, -4, and 1, -4. Then what I did is I made a number line, and I put those 3 x values, the -1, the 0, and the 1, on the number line, because those are my critical values, and those are the places where increasing and decreasing may change. I also put the y values up above in case I needed them. It kind of makes sense that it would have to be increasing between -4 and -3, and it would have to be decreasing between -3 and -4. But we'll plug into the derivative just to make sure. So that's what I did. I chose -2 just as a simple point to the left of -1. When I plugged -2 into the derivative function, I got -24. So sure enough, to the left of -1, the derivative is negative, so the function is decreasing. Then I plugged in -1/2 to get something in between -1 and 0. When I plugged in -1/2, to the derivative function now, I got 3/2, which is positive. Therefore, my function is increasing between -1 and 0. Next, I take positive 1/2 to get something in between 0 and 1. When I did positive 1/2, in the derivative function, I got -3/2. Sure enough, it's negative. The function is decreasing between 0 and 1. Finally, to the left of 1, I chose 2. In the derivative function, I got 24, which is positive, so the function's increasing. And then, of course, I put my answer in interval notation, so it was increasing from -1 to 0 and from 1 to infinity. Round brackets because at those local minima and maxima, it's not actually increasing or decreasing. The slope is 0 at those points. And then decreasing from -infinity to -1 and from 0 to 1. So I did graph my function using Desmos, and you can see that it is decreasing, then increasing, decreasing, increasing, decreasing, increasing, and yeah, at -1, 0, and 1 are my two minimas and my maximum. The last problem on this page is a logarithmic function, and we're going to see when that is increasing and decreasing. So I created my own logarithmic function for this one. My function is the natural log of 2x squared minus 18. I took the first derivative. Don't forget my chain rule. And I got 2x over x squared minus 9 after simplifying. Now you can't see that really well. Yeah, there it is. So then I set that equal to 0. And it's equal to 0 when x is 0. Plug 0 back into the original function, and oh, we can't take the log of a negative number. So I need to go back and take a look at the domain of this thing. That 2x squared minus 18 has to be positive, or the function doesn't even exist there. So I went ahead and solved for that in the domain. And the domain exists where x is less than -3 and greater than 3. So the 0 of my derivative isn't even within the domain of the function. So my derivative does not have any zeros, so I don't have any relative minimas or maximas. So what I can do is plug in numbers on either side of that big hole in the domain. So I put in -4, and I got -8 over 7. I plugged in +4, and I got 8 over 7. I did make a number line. And you can see on my number line that I put this whole domain exclusion. I don't need any of this. And -3 and 3 aren't included in the function either. When I plugged in -4, remember I got that -8/7. So this is negative, and it's decreasing to the left of -3. I also plugged in 4. I got a +8/7. So it's increasing to the right of +3. And yeah, nothing's going on between -3 and 3 because the function is not defined there. So I did end up graphing that same function in Desmos, and you can see this big gap between -3 and 3. You can see that it's decreasing on the left side, and then it's increasing on the right, just as I predicted with the algebra and the calculus. So that's it for the 4th page of that packet.